And I'm live. That is cool. Today is 6th of September 2025, Saturday. And in today's stream, we are going to build some library or sort of library like thing of our own, in which we are going to implement binary search tree. And you can see that we are serious. I have this whole thing. So these are the things that a binary search tree is supposed to have. These are the operations. And before we begin, what is a binary search tree? A tree, let's see what a tree is. A tree is a graph in which you have some nodes, and the count of those nodes is n. You have n nodes, and in a graph, there are connections between nodes like so. And the special property of a tree is that you have n minus 1 connections, first of all, and second of all, when given these connections, you can start from any node you want and you can end up at any other node, either directly or indirectly. That is, for example, and a tree does not form a circle. Right? Here there are 4 nodes and there are 4 minus 1, 3 edges. But the thing is, here we have a circle and there is no way to reach this node. So therefore, this thing is not a tree, but something like this is a tree. You can reach any node starting from any node, and yeah, there is no cycle in the thing, and total number of edges is the count of node minus 1. So that is a tree. And now binary. What is binary? Binary here means something like this, 5 nodes connected like this. These are also, this structure is also a tree because you can reach every node starting from any other node, first of all, and second, there is no cycle. So this is a tree, but this node has 4 connections to it. In binary tree, we have a node and then there are some children node, there is a hierarchy, and a given node at max has 2 children, not more. It might have no children or it might have a single children. Here this node has no children, this one also has no children, but this one has 2 children, left and right. This one has 2 children, left and right. This one has a single children and a single child. And yeah, that is the thing. Binary trees. Every node either has 2 child or no child. And 2 child, 1 child or no child. And then search. The search part here means if you have a node here and there are 2 nodes connected to this node, this node might have a key value, let's say 5. So this node on the left has to have a value that is lower than 5. It might be 2, 3, something like that. And on the right, you have a value that is higher than 5. Every value of every node that is to the right of this 5th node has a value that is higher than 5. And every node to the left of this 5 node has a value that is lower than 5. So that is the search part. Therefore, we have a binary search tree. A tree that is binary, and there is this property about the keys. A key might be lower and higher. The values of keys to the right of a given node is higher, and the values of the keys to the left of a given node are lower than our starting node. So that is binary search tree, and these are the operations that a binary search tree performs. Search, given a single key, our tree class, we are going to create a class for this. Our tree class should be able to tell if this given key exists or not. and we can call the minimum operation on our tree, which will return the minimum value, and the maximum operation, which will return the maximum value that is in our tree. The successor operation that will return the next smallest value from our key. If I have k, then if there is a key k plus 1, this should be returned. And then there is the predecessor, which is the opposite of that, which returns the given a key k, this predecessor will return the greatest key that is lower than the given key. And insertion inserts a given key into our table, and then deletion. Deletion is the hardest among all the operations because you have to see some things to make deletion work. You have to make sure of some things. And now, given that, we are going to build our binary search tree, and let's see how it goes. Okay, let's go to the right folder, projects. I do not call, we cannot call this projects. Tmux set. I will set up my Tmux attach tbsc cd cdds and binary, or we can write just bst.cpp. Yep. Here we have our file. We are going to initialize a class. It will be called binary search tree. And yeah, this is not supposed to have these. And the methods that this class needs to have are search, minimum, maximum, successor, predecessor, insertion, and deletion. So we have the search method, which is going to return an integer and search, and it will take in an integer a. And then we have the yep, minimum, maximum, successor, predecessor, minimum operation, which is not going to take anything. Then we have maximum, which is also not going to take anything. Then we have integer successor, which is going to take integer a, let's say. And predecessor, this is also going to take an integer. And then we have insert, which is going to not return anything, but will take in integer. And void delete. I think we cannot write a function named delete. Yeah, let's call it remove. So these are the methods that we have to uh, create in our class. And let's create, before this, a structure node is type def struct, and this is going to have integer key, integer key, and wait, and node struct node pointer called parent. It is going to have a parent, and struct node pointer left child, struct node pointer right child. And do we need anything else in our node? I don't think so. In our node, every node that is connected in a structure, every node is going to have a few things: a key, and key is just like a value, right? We can make our binary search tree more advanced, in which it will also handle other data types like other than integers, strings and stuff like that. But for now, we are only operating with integers. So it is going to have integers and a parent pointer, which is going to tell us who the parent is of this current node, a left pointer, which is going to tell us the left child, and a right pointer, which is going to give us the right child. And initially, all of these are null. Right. So now we have to, whenever we initialize a binary search tree, we have to write its constructor and a pointer. All we need to work on a binary search tree is a pointer to the head, and initially that pointer is going to be null. So a function, not a function, but a node pointer head, and it is private. Now we have void binary search, or maybe instead of writing binary search tree every time, we can write BST, not BTS. Void BST binary search tree, its function BST is not going to take, does not have a return type. Cannot have a return type. Okay. Implicitly, definition of implicitly. BST, and it is not going to take anything. And here we have to initialize head equals new node, and we also have a destructor BST, which will also take nothing. It will just delete head. Now we have to define the other functions. First of all, let's define search. Search is going to be nice. Integer BST search int a, and then the whole body. And integer a is an integer, right? Tiny old hello good morning. Nope, I don't know ADSA. Mm, methods and functions. I mean, if you are learning for the first time, if you do not know what binary search tree is and your language is giving you facilities so that you do not have to write binary search tree on your own, then getting to know what binary search tree is and how it works is nice. And when you know enough and when you feel comfortable, maybe you can delve deeper and write our own function. So it is not bad if it is helping you, so that the complexity of the data structures is not getting in your way of learning. If you can learn and if it is helping you to learn in that way, so that is cool. Do not feel bad about it. Using Python for data structures. And yes, now search. We have the head. Head points to the first node. First, we have to check if head equals nil, nil or null pointer. Initially held Initially, head does not equal to anything. That is how we initialize null pointer. And when we are implementing the search method, first we have to see if the head is null or not. If head equals null pointer, then what is going? We need to have a type. We need to have a number which represents that we didn't find a thing or something does not exist. That is what we have to return. Let's for now use -1 for that. For now. Now, if the head is not null, then we have to go while head. Now we cannot change head auto c equals head while c inside c key isn't equal to a. If c dot key is higher than the search value, if it is higher than the search value, then c is has to be equal to c dot left. If a does exist, then it has to be on the left side. And yep, delete key. This is not a right thing to see. If while c is not equal to null pointer. Yeah, that is the only thing we have to check for. Else, if c key is greater, if the current key is lower than a, then a c has to go to the right. And if the current key is higher than a, then c equals c dot c go to left. Else, if it is equal, then break. Yep. And when we are out, if c is not equal to null pointer, then we know we found the value that we were looking for. Then we can return a. Else, return -1, -1 for now to indicate that we didn't find the right answer. So this is cool. This is cool. But I do not know what the point of this thing is. Yes, we can return a boolean instead. Returning a boolean is very cool instead of returning plus and -1. False here and return true, return false. Now we have this function working, but we cannot test it right now because we haven't implemented the insert method. Let's implement the insert method so that everything that we write, we can at least test it. Void BST insert A. And this is going to work to insert stuff. Hey bro, hello, yo, water, how are you? Long time no see. No, I'm living at home and I do not go to college. I just live at home and try to study. College is bad. College wastes time. There is no point in going to college. I mean, the college cannot teach you anything. Yeah, you can learn everything that you can say that college teaches you at your home at a faster pace and at a better quality. So going to college is like no good. Insert. Now, we have to insert this current thing. at some place. So auto, the current node, is going to be equal to head, and while c isn't equal to null pointer, what we will do is if c greater, if c is greater than or the value at c, if the value at c is greater than whatever the value is at a, then c equals c left. Else, if c is key, the key at c is lower than a, then c equals c right. We have to increase c. Else, if they are the same, then break. We are not going to have copies of things. So this is going to be sort of like a set. Now, if c equals null pointer, then we can do, we have to initialize a new thing. Auto x equals new node. Auto x equals shit. The destructor that I created here. This is very bad. This is very bad. We have to perform DFS on every single element on every single node to clean it. The destructor is very bad. It is going to leak a lot of memory. And x dot e, make it equal to a, and x left equals x, right equals null pointer. Even though I didn't have to do it, we can make it equal to null pointer. And then we cannot do c, right? Remember, we cannot do c. So how do we keep track of the thing that we had previously? P equals head, both of them equal to head. And whenever we do something like this, we are going to do before this the break is cooler, and before updating c, we have to make p equals c, so that we have the last thing that c was equal to. Yep. Now p is there. P dot, okay, and also if p, the key at p key is lower than whatever the value is at a, that is a is greater than p dot the right thing equals x. Else, if it is lower, and it is never going to be equal, if it is lower than p left equals x. I think that is fine. I think that works, I hope. Is there attendance thing? Yes, there is attendance thing, but I just ignore it and do not go to my college, because what can they do? They cannot do anything. And I also don't like to go to college. 75% mandatory, so I have to go. I mean, I also have to go in the way that they say it, but I do not go there because this thing is more important to me. Studying is more important than maintaining attendance in a college. I cannot blame that I had to go to college and then not study at home. I cannot blame my college for that. And it is a total waste of time. Yep. 6 to 8 hours, teachers yap. Yep. Yep. We don't get anything that they are saying. And there are a few subjects which I don't like and don't attend. And lots of views. Yep. They're just increasing the count of the subjects. And like there is no point. There is no point in college. You can learn much better things at a much faster rate at home. There is no point in going to college. Okay. We have created the insertion thing. And yes, I think this works. I think this is going to work. So let's write a little program while true, and we will initialize auto BST equals BST has a private destructor. Shit, 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 shit. Okay, my bad. I think that is cool. Yep, that is cool now. While true. Now, yeah, we will take in a char C. Enter I for insert, and yeah, for now that is all that we have. And C in C, include bits std c plus plus dot h, and using namespace std c, and here if c equals capital I, then what we are going to do is bst dot int a and c in a and b dot insert a. But how would we know if we have inserted anything? We can use our debugger for that. Clang plus plus binary search tree out or BST with the flag G LLDB BST. Let's run it. Set a breakpoint at main and run. Yes, that does work. Next, step inside. Next, I for insert. Next, now we are in, and now it is asking for a number. Let's say 42, the answer to the universe. And now we are calling our insert function. Okay, we are inside the function. We are inside our insert function right now. No, our thing stopped. Our thing stopped. We looked for P key. That makes sense. We are not checking in our insert function if head is already null. If head equals null pointer, then head equals new node and head e equals a and returns. Wait, yep, clang again. LLDB BST breakpoint at main run. Next, step inside. Next. Oh, yes, it is asking for a number, and now it is asking for a number. Let's say 42 again. The answer to the universe. Print B. What do we have inside B? We have a pointer to head. Okay, shit. How do we see the value that is stored at a pointer? Can I start my CP journey in Rust? I have seen threads on Reddit which say that starting CP competitive programming in Rust is not very good. You can start, but you cannot get very far ahead because the I mean I do not know how things are in Rust, but the claim is that in Rust the way to handle things is very bad. The way to handle data structures and trees is not very good. And yeah, that is what I have heard. You can check on Reddit. So yeah, you can see on Reddit. They cannot stop me from giving the end semester exams. They can stop me from giving the like exams inside college, but they cannot stop me from giving the final university exams at the end of semester. So that is cool. I'm using Vim. Yep, Vim is pretty cool. But we have a problem here. We have our head at this pointer, which is a node, which is a pointer to a node. But we do not know how we can see the thing that is at that pointer. So let's see how to mm, access pointer values in LLDB. Print my pointer. Shit. Okay, that is cool. That is that cool. Print go to my pointer. P my pointer. Okay, let's print go to B dot head. Shit, we have the thing. We have null pointer here. Okay, that is cool. We have the value 42 here. And now, where are we? Next, 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 insert, next. And if I write 37, next, no crash. Okay, that is cool. Let's print B go to B dot head. Okay, at B's head, the key is 42, and on the left we have a pointer. Let's go and see what is there. Head dot left. Okay, shit. That makes sense. That makes sense. Yes, there is 37 there. That is cool. LLDB is very smart. LLDB fixed my mistake on its own because here I did go to B dot head. This thing will return this thing. But inside there, I had to use this thing to get to the left side of this current node. This is very cool. And if I insert 37, I should not get anything. Next, 37 again. Next, print go to v dot head. Okay, so on the left, we still have a left pointer, and there we should only have 37. Print go to v dot head, it's left, and we only have 37. That is cool. That is cool. That is cool. That works. And our search would also work. Shit, we can add our search function here also. Enter I for insert. And yeah, I thought so. We cannot do this. Can we do this? How to give multi-line string in C++. So multi-line shape. Okay, I can use this notations. That's cool. C out, enter. I for insert, and then yep, I for insert and S for search, and then enter your option, whatever it is. Let's see, and okay, we also have to write a choice. If C equals S, if we are searching, then int A, C in A, but before that, enter number to search for, then we will have A, and then we will call B dot, if B dot search A, if we find A, then C out, number was found, else cout number is not in the tree. Okay, and also here we dot insert. This should insert shit. When I'm calling here, I have to change everything here because when I'm calling here new, I'm just supposing that new works and I do not have a pointer, null pointer. Shit. I need to have unique pointer to these things. So I have to change this. I have to change this unique pointer. We are going to use unique pointer to structure of node, and same for the right side. C's right and left. Okay, and also we have to change how head is. Head also has to be a unique pointer of node, and if that is the case, then I do not need anything. I can just do head dot reset. Okay, unique pointer, you cannot do stuff like this with unique pointer. Okay, that is bad. Shit. We have to use shared pointer. Substitute pointer with shared pointer. Okay, now we have shared pointer. That is cool. That is cool. And I just have to change the notation. If head is null, then return. Yep, here I'm not allocating any memory, but here I am. Head equals convert shared pointer or shared pointer or make shared pointer. Head equals make shared for type node pointer. And what do we have to make shared? New node. No viable overload. How to allocate memory to shared pointer in C++. Okay, we have to see a lot of stuff. Make shared, that is what we are using. Shared pointer equals make shared. Here is the type, and inside we have 10. Okay. Node 1. And are we allocating any other memory? We also have to change the type of the parent. That makes sense. And here, why do we have this? Dot right equals x. Yes. Shared pointer. Shared pointer to a node called x equals make shared of type node, just one thing. And std, of course. Yep. Seems all right. And I am calling shared pointer here, and we are making the left and right equal to null, but also we have the parent thing which we have to fix. Shit, yes, we didn't fix it. X parent is p. Yes, that is correct now. And here also we are doing the same thing, but we don't need any parent. Parent can be equal to null. So head left equal head, right equal head, parent equals null pointer. That seems cool. Yo, there are slow learners who take time to understand things. Yo, yep. And the editor is NewVim. NewVim is amazing. Look at this. This is amazing. Pretty amazing. I can do a lot of things with this. And yep, currently I am pupil, but there is a contest tomorrow. Well, I'm not going to become expert in tomorrow's contest because I'm just 1200 plus something. So not tomorrow, but yeah, in some time I will become a specialist and then expert, or is it the other way around? First you become a expert and then a specialist. But yeah, my rating will increase because I'm working hard and I want to increase my rating. And getting back to this thing, we have our insert operation. Insert operation is now memory safe. No memory is going to leak. So that is no, shit, that is not cool. That is not. No, memory is going to leak. Memory is going to leak. So we have to fix the destructor. Destructor cannot work like this because we have cyclic dependencies, and yes, we have cyclic dependencies and it is not going to be fixed. So we can write a more sophisticated DFS based destructor later in a while. Before that, let's check if this thing is actually running. Client plus plus BST and dot slash BST, enter. Okay, first let's search. Actually, search, we are searching for the number 20. Oh, there is no number such as 20 in the list. And we messed up in printing the thing. Okay, so there is no number such as 20. So let's insert a number. Let's insert 20. Okay, it has been inserted. Let's insert 37. Okay, let's insert 42. Okay, and now let's search for 37. Number was found. That is cool. Now let's search for 20. Number was found. Okay, we also added 42. Number was found. So we looked for 42, 20, and 37. They were found. Now let's look for 10 and 10. Insert, search, enter I, insert. Oh, okay, we messed up. Shit, we had to. Yeah, shit. Okay. Search, search for 10. Number is not in the tree. So that is cool. And there are also some aesthetic things that we have to fix. Search, enter number that you are searching for, and insert. Enter number. And apart from that, when we say that the number was found, let's give a new line at the start, or maybe, yeah, one new line is fine. And then here, two new lines. And here, two new lines. And here also one new line. And this should be more aesthetic than before, than how it was before. BST insert 42. Insert. Okay. I need new lines here also. Enter number. And here also before this thing, a single new line will work. Client dot slash BST. Right. Um, let's say insert, enter the number 42, insert 37, 27, insert 37, and search for 27. Number was found 27, yes, because it was there. And now search for 10. Number is not in the tree. So it is working. It is fine for now. Insert operation is working fine. Search is fine. Insertion is fine. Let's go to minimum, maximums, and then we will go to successor and predecessor. Data structure classes, our professors made us to do such menu-driven program for each data structure. Thus, great way to learn both the language and the data structure. Yep. Oh, 8 spaces indentation is amazing. Like, look at this. And these are not even spaces. This is not a tab. My tab have been expanded into spaces. So I can roam around in the free space. Look at this. That is crazy. Now we have to write more functions. Integer, BST. Let's go write minimum, and it is not going to take anything. If head is null pointer, then return -1. Otherwise, auto C equals head, and also auto P equals C. P as in like parent, and we'll keep while C is not equal to null pointer. What we'll do is before moving C to the next left thing, P will make P equals to C, and C will become equal to C's left child, and we will exit when P is the leftmost node and C is null. Then we will do return P K. That is minimum. That should work. And BST maximum. It is not going to take anything. It's similar thing from before, but I will not copy paste. Let's just write it out. If null pointer, then return -1. -1, we are using -1 to represent that we didn't find the thing. -1 is not very elegant because if we are using -1, then we will not be able to store keys which have a legit value of -1. Why C is not equal to null pointer, P equals C and C equals C. Right, we are going to the right and then return P, not right, P. Okay, now we have functions written for looking for maximum and minimum values. Mx or Mn, maximum, new line, and Mx, I messed up, minimum, and here maximum. And we will search for C. Else if C equals, that is a dilemma because C is a character. Makes sense. M for minimum and X for maximum. Int A equals B dot minimum. And if A equals -1, then we can see out tree is empty. Add stuff. else cout minimum. Minimum number is a. Yep. And we have to do the same thing, about the same thing for maximum when it is equal to x, when the input equals x dot maximum. And if a equals -1, that is we didn't find a thing, we will write tree is empty and stuff the same line from before, but we didn't copy paste the line because we are going to write it again. And here maximum number is a. I think that is cool. That should be cool. So let's search for the maximum. Tree is empty, add stuff. Minimum, shit, nothing is there. Okay, let's insert 37. Let's insert 42. And now what is the maximum? Okay, M is minimum and minimum is 37. That is correct. What is the maximum? Maximum is 42. That is correct. Now let's add a bunch of more random numbers. Insert, 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 insert. And what is the minimum? Minimum is 37. What is the maximum? Maximum is this number. So it is working. It is working. Why I spent so much time and so much time in programming? Yep. I'll say because I'm swimming in free space intended. Yeah, yeah, you can say that. You are swimming in free space. Look at this. Look at this. Free space. Shit, it is already 150 lines long. Okay. Now we have written a few functions. Inserter is done. No, yes, inserter is done. Minimum is maximum done, minimum done, search done. Now we have to write successor and predecessor. For this, we have to know what is in order traversal. Yes, we are going to use in order traversal. If given a node like this, if our BST looks like this, then in order traversal, we start, let's give the numbers 1, 2, okay, that is wrong. Remove the numbers, remove the numbers. Here is a node, yep, and here are other nodes. Here we have 1, 2, 3, 4, 5, 6, 7, and you can confirm that this is a correct binary search tree. And if we go in order traversal in this, we start from the leftmost node. We start from this node and we call our in order traversal function on this node. And if this node has a left child, we call our in order traversal function recursively on this child. And since this one also has a left node, we call our in order traversal function on this child. And this is the smallest number. So, and this one is a leaf. It doesn't have a right or a left side. So we output this, we print this, and then we print this. Then our recursive function, which we called on this, returns, and we are back onto this. And this one prints the current value, which is going to be 2, and then calls the function in order traversal function recursively on the right child if it exists. So it is going to be 3, and when this is done, this function which was called returns, and we are back to this, which returns the key of this current node, root node, and we have 4, then calls the in order traversal function on the right node, And on the right node, first we have to call the in order traversal function on the left node, which is 5. And when we call this, the function on this, the key of 5 is returned. And when the function returns, we go back here and we print the value of this current node, which is 6, and call the in order. Wait a minute, I'm getting called. Now it is fine. Is my camera working still? Yep, camera is working. Things seem fine. That is cool. I've been learning Python and I am in between beginner to intermediate. I am in class 11th right now. Which college are you in or passed out? Sure. How are you able to code when you are in 11th? When I finished my 12th, I didn't know how to write hello world in Python. I'm from India, and I guess that is obvious, but I'm from UP right now. Yep. And which college? Yes, I am in college, a local tier 3 college. I don't even go there. And yeah, that is that. And stream health. Yep. And let's, so yeah, we now know what is in order traversal. 7 would be printed as the last thing. So we have to write a recursive function for in order traversal. How do we do that? I think we cannot keep calling the method. We have to write a function separately. We have to write the function separately. Let's write the function here. And if I write some lambda function, auto in order, let's say it is equal to some lambda function, which takes in nothing, which takes in a number a and return 1, let's say, can I say after this BST in predecessor equals in order? No, but I can call in order function internally. So that is cool. So let's write this lambda function. This not we are not going to write it as a lambda function, but as a full-fledged function, so that we can also use this outside. DFS on each node perform this function now in order. In order, and it is going to take in number a, and also no, it is not going to take a number a, it is going to take a number a, and it will also take in a standard shared pointer to a thing called node, which we will denote by p. And yep, it is looking for the successor in order traversal. So what is this function going to do? Predecessor and successor. If the current node has no left child, it's difficult. My Indian student interested in tech and programming to build skills, as we are pressurized to prepare and score well in JET and JEE NEET, but I have interest in programming and AI/ML. You can learn AI/ML and programming, but I managed somehow to take out 1 to 3 hours a day. That is grind. That is grind. That is grind. So yeah, work hard, right? Work hard. And even if you don't get a nice college, it does not matter as much. More important, the thing that is more important is programming. And if you are getting better at programming, then it is pretty cool. That would be pretty cool. Okay. In order traversal, let's go down here. 13. No, no, even below that. 18. Yep, here. we will have, this will return integer, BST, predecessor takes an integer a, and yep. First we have to find where a is. And how do we do that? I guess internally we have to change the structure. Let's say instead of returning the integer, we should return the pointer to that integer. Insert, we don't have to change anything inside our insert function. For search function, should it return boolean? I guess I can write my own implementation here. Okay, if head equals null pointer, then return -1, and we are using -1 as some -1 as to mean that the thing does not exist. Currently it is null. And then auto c equals head and auto p equals x. Let's say c and c. Now we have to search for this number a. So while c dot key isn't equal to a. So here we do know for a fact that this thing exists, or maybe we can check. We can check beforehand. We can call search a, and if a does exist, then we will continue with our search, else return -1, no predecessor. Or maybe not just this, by predecessor we might even mean any number that is smaller, the biggest number that is smaller than our given number. That makes sense. That makes actually quite a bit of sense. That actually makes quite a bit of sense. Or maybe that would be something similar to lower bound or upper bound, but let's not make it more complicated at this point. It is not very complicated right now. Let's search for a in our tree, and if a exists, then cool, else not cout but return -1. And in here search a. If a does exist, then first we have to find a, and then it's in order traversal. Auto c equals head, and we will move our head while c key isn't equal to a. If c key, if a is greater than the key, then a must be on the right, so c equals c right, and else c goes to the left. C equals c left, but we might actually be at the key, right? If c, no, c key is not equal to the thing. Yep. After this, c will point to the thing that we are at. Now, if c does not have a left child, then the answer is going to be the parent. If c left equals null pointer, then return the value at c's parent. Go to c parent dot key. Else if left does, wait, we are talking about predecessor. Yes, predecessor is back. Predecessor is back. If I am here, there is the parent. left child and right child, and if I am currently here, then the predecessor, the thing that came before me, is going to be lower than me, that is on the left. Now if left child does not exist, then the next thing, or if the left child does not exist, then there is no predecessor. Shit. If the left child of the node does not exist, then there is no predecessor. There is no value that is lower than this. Huh, that makes sense. Returns -1. Else, if there is a left child, then we have to find the minimum value in that thing, or not the minimum, but the rightmost value on the left subtree. That is the maximum value on the left subtree, which is easy. Shit, which is easy, which is easy. We can call the maximum function, but internally, shit, we are here always calling the maximum function on the head node, but we can write it as a general function and make our thing easy. Okay, we can make our lives easier. Maximum key. It will take in a integer a, and it will also take in std shared pointer to a node called p. And internally, what it does is, if p equals null pointer, then return -1, else the same thing that we wrote here, not head but p. Now we have two p's, so let's call this one n. Now we have this is for the minimum value because we are going to the left. We can write this as right, and internally in this function we can call that function return maximum key for integer. Why was I even taking n? Why was I even taking a? We don't need a here, we just need a node pointer. And a similar minimum function, minimum key, for which we are always going to go left, the leftmost thing, and yep, the leftmost thing. And internally here we can return minimum key on the head, whatever the value is. And in our predecessor function, if left thing does exist, then the predecessor is going to be the maximum key on the left subtree. So return maximum key on the left subtree, which is c left. So predecessor does work. Now we also have to write successor for in a, and we will do the same things that we did in the other function. Gold mine of knowledge. Thank you. Hello, how are you? I've seen your previous live streams, especially the boot backend one. Shit. Okay, I didn't even complete that course, but thank you for watching that. Do you think is it worth it to buy the subscription? No, I don't think so. How your experience overall using boot dev? Like, I wanted to start learning backend development. Yes, boot.dev is like, it is the genuine thing. It is the real thing. You can start from boot.dev if you want to learn backend, because there I've taken their Git course completely, and that Git course by Primeagent is amazing. It has everything. It is not just going over the surface. It explains how the things work internally, which is amazing. And I would recommend that you take that course. Since you are already taking that course, you don't need the recommendation. But the thing is cool. Yep, I did both the parts, part one and part two of Git. It was amazing. In third year, mastering Java full stack, should I learn competitive programming? Competitive programming is going to help you no matter what you are doing. I made a very shitty video on my NeoVim setup, and that was very bad. I did a live stream on my NeoVim setup, and that was very bad. And about competitive programming, yes, it is going to help you no matter where you are in your journey, because it makes you more, you could say, witty in the sense of competitive programming or programming in general. You are able to recognize patterns much faster than a average person. And also, what is this? And yeah, you get a better problem solving mindset, which helps you. And yes, I think I will make a much better video, but not this year, on NeoVim. You can go to the Discord server that is in the description, and there are resources for learning NeoVim, and they are amazing. I used them to learn NeoVim. You can also check them out. And doing CP31 questions today. Yep, there are some questions in CP31 that I'm going to do because there is some streak going on. I'm going to complete the previous questions which I was unable to do. There are 2 questions remaining at 1300 level which I haven't done. Series high struggling. Any suggestions? Yes, there is going to be struggle. I was, when I started DSA 3 months ago at this point, I was struggling at questions, build completely basic questions. I was struggling on completely basic questions like binary search, questions that are at 800 rating, and I'm still struggling at questions of 1400 rating. So you are always going to struggle, just keep at it. It is very hard to do, keep at it. Yesterday I didn't study anything. After the stream, I just watched YouTube videos and didn't study anything. That was pretty bad, but now I'm trying to be focused and study. Concrete skills or good college? No, concrete skills. College does not matter. How would a college help you? The only sense that a college can help you is you can make good friends. And by good friends, I mean people who are into programming. And from the college that I go to, tier 3 college, I have found a bunch of very good friends. So I don't need the college anymore. The college has served its purpose. And people, yeah, people, getting to know people is the only thing that the colleges are good at. And yeah, you do not need to be in a good college. Concrete skills matter more. On ID setup, shit. Okay, yeah, I would suggest that you go and check the things out in the description, in the server's resources. That would be cool, because making a video on NeoVim, it I can make a video on NeoVim, but I would not do a very good job on explaining how NeoVim works. There is this guy named, let me show you, VHYROO, something like that. Understanding NeoVim. This series, VHYROO, you can watch this series, and this is very amazing. Like I cannot create a video series like this. This is very, very amazing. He explains what are plugins, what are color schemes, how to install NeoVim. He takes 20 minutes just to explain how to install NeoVim. So this series is highly recommended. You can check this out. Series, yes. For that, I have things in mind for instead of live streaming, making a series. I have things in mind. I'm learning, not currently, but I am going to learn how to do video editing, and next year I will start making videos, because for now competitive programming is the main goal, since I have to reach a rating of 2000. That is pretty important. And now back to this thing. If head equals null pointer, we are looking for the successor. That is going to be the smallest value that is greater than our current value. If null pointer, then return -1 if we do not have anything in our tree. And if we do have, then search for it. If search A, if we do have this key A in our tree, then look for it. C equals head, and while C is not equal, C key is not equal to A, what we will do, if C key A is greater than the key, then A is going to be on the right. So C equals right, and else C equals C left. C is going to be on the left, and yep, after this I should have C pointing to A. Now we need the successor for this thing. Yep, we need the successor for this thing. And what is the successor going to be? Int s equals, successor is going to be the minimum value, called the minimum key function on C dot right, the minimum value that is greater than C. And now if s equals -1, that is, there is no minimum value to the right of C, then return -1. I can just directly return this. I don't even need to know the value. Else, if A does not exist, then return -1. And we can write this in our function here. S successor. Let's use N for next and P for previous. And here, else if C equals next in A equals, or no, yes, in A and C out, enter the P. But before that, a new line would be pretty nice. C in A, and today feels to be just one of those days when the brain is just not working. I'm functioning through my back end, you could say subconscious. I'm not very conscious of what I am doing right now. Anyways, if A, okay, we have A, we know whose successor we need to find. Say int s equals b dot successor. Next is successor of A. Now if s equals -1, then we didn't find a successor, so C out no next node, else C out next node found, and it is S. And the same for else if C equals P for previous int A C out backslash. What is that? Uh, New line. Enter the key. And when we have the key, which we are going to take using cin, now we can call int p equals b dot predecessor on a. Now if p equals -1, then cout didn't find the didn't find or no previous node. Else cout previous node, which is going to be p and a new line. Next node. Okay. Hmm. Let's see if it works. But before that, is there something that I would like to change? No, looks fine. BST. Let's insert or let's see what is the next node. Enter key. Okay. 3. No next node for 3. Okay. Let's insert 42. Insert 37. Insert just random nodes. Insert 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 and now insert 200. And now let's find the next node for 2000. No next node for 2000. So therefore 2000 must be the maximum node. Let's see. Maximum is this. Okay, so we messed up. Mm, We messed up. We messed up. We messed up somewhere. We messed up somewhere. In today's era of AI, which is taking every entry level job somewhere. Which matters. Yeah. Developer skills. I'm 1250 on ad coders, 1440 higher than me on code forces. I'm struggling in this level. So I guess you just have to read more things. I have seen that when you are unable or when I am unable to solve questions, then I have to stop solving questions and read some things. Maybe read some stuff from, wait, is my internet fine? Yes, my internet is fine. Read some stuff from competitive programmers handbook. It is not showing up right now due to some reason. Competitive programmers handbook. Go there and read some things. Book.pdf. Yep. Go to competitive programmers handbook, read some things. And is that series dependent only on macros? No, it explains all the things in NeoVim. How to, yeah, all the things. What is an LSP? What are tree sitters? How does syntax highlighting happens? Everything is there. So that is cool. No, I haven't gotten any placement opportunities. I'm in college and I haven't applied to anything, but there is a mistake with this thing. Let's search for 2000 and node was found, but why don't we have a predecessor or successor for this? Let's find predecessor for a node that we know for sure that we entered, which is 42. 37 was the predecessor. That is cool. But there is some mistake that we have done in our code, in our function, in successor and predecessor. We find the node, all right. We are in a BST, binary search tree, and we are looking for the successor. Successor or predecessor. When we are looking for the predecessor, it is always going to be on the left. And if we look for the predecessor, previous node for 2000, no previous node. That is kind of crazy. No, it isn't. No, it is not crazy. No, it is not crazy. If the left node does not exist, then the predecessor would have been, if this current node is the left child of its parent, then the successor is no, the current node has to be the right child of its parent, so that the parent has a lower value than this current node, and that is the case when there is no predecessor. So that is cool. Okay, so let's fix that. Wait, why is the code for predecessor so larger than the code for successor? When head is null, then cool. But if A, yes, if A exists, then find A. After finding A, C, then left is null pointer. If left is null pointer, then C. If what the parent is, if P, if C parent is not equal to null PTR, then return C parent E, else return -1. But if the left thing does exist, then return the left thing. Or if both of them exist, then what are you going to do? If both of them exist, then what? That is a nice question. That is a very nice question. So if left exists and the parent does not, if left does not exist, but the parent does exist, then this, and here left does exist. Now we ask the question if the parent exists or not. If parent equal null pointer, then return the maximum on the left side. Wait, we are going to find the maximum anyway, so maximum equals maximum key for C left. Now, if the parent exists, if the parent does not exist, then return mx. Else, if the parent does exist, then return the minimum of the two, minimum of parents key comma mx. Why is it float? Why is it flow? We have included that library, so why do we have this error here? Use of undeclared identifier minimum. Return mx if mx greater than C parent key, then return mx, otherwise return mx, otherwise C parent key. I don't like doing this thing twice, going to C's parent and then finding the key. I don't like that. So int p equals C if we don't already have been used the p variable. Then return p, first ask if p is greater than mx. If that is, then return p. We are looking for the minimum value. Then return mx, otherwise return p. And we have to do the same with the successor thing. Find a. After finding a, c. If now we need the successor. So the successor, and also the parent could be left parent or right parent, or the child that we are at could be the right child or the left child of the current parent, which we have to check for. Shit. Okay. Here we are accessing the parent. If parent is not null, here we have to see if, okay, parent is not null, then let's say auto p equals c parent, c parent. Now we know that the left child does not exist, and parent, if parent dot, if parents, this current thing, we want our current node to be the, since we are looking for predecessor, we want the current node to be the right child of its parent. If parent right is not equal to null pointer and parent right e e equals a, equals a. If that is the case, then return the value at parent. Okay, that thing is handled. And here also we are accessing the parent. C is parent. If parent does not exist, then return mx. But if the parent does exist, let's say auto p equals c parent. Now we have the parent. If we want, if p, we want a to be the right child of p. So if p's right child is not equal to null pointer and p's right child equals the value at a, and p's key, if p's key is smaller than mx, then return key at p dot right key, else return mx. Okay, so shit, there are still some scenarios in which we are not returning anything, it seems. Right here, return minus, return -1. Now, now it is cool, right? There are still two errors though. Here in the successor function. Now, when we have found C, we want to see if C has a right child or not, because the next successor is going to be on the right. If C right is not equal to null pointer, that is, the right thing does exist. Therefore, int mx equals maximum key, call the maximum key function on the right side of C. Keep that. And now we have to talk about the parent. Auto P. First, we have to see if the parent does exist. Now, C. If parent is not equal to null pointer. I guess we don't have to check against null pointer. We can just say if C parent, but let's not take any risks for now. If C parent is not equal to null pointer, then the parent also exists. Then C parent equals C parent. When we have the parent, now we will only return the parent if C is the left child of the parent, and if P's, yes, if P left is not equal to null pointer, that is left child of P does exist and P's left child is A and P's key is smaller than mx. If that is the case, then return P's key, else return mx. And here we are looking for the key. And now, else, if that is not the case, if parent is equal to the null pointer, if parent does not exist, then we just return whatever maximum we find, and here return -1. If the right child, no, it is not that simple, it is not that simple, it is not that simple, shit. In the else statement, we have to see if the parent exists or not. If the parent exists or not. If the parent exists, that would be P. P. Yeah, cool. If C parent is not equal to null pointer, if the parent does exist, then or not C out, but return parent key, else return -1. The parent does not exist and there is no key. Low key. That seems about fine. And yep, that seems about fine. Let's test our theory. Climb BST dot slash not out dot slash BST. Let's insert few random values. 14. Insert, 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 insert. And now let's insert a value that we know. Let's say 50,000. 50,000, right? And let's find the previous value for 50,000. No previous node. That is wrong. That is completely wrong. Okay, so what is the next node? Yes, of course, no previous node for 50,000 because 50,000 does not exist. No, 50,000 does exist. Search for 50,000. Node was found, number was found. So 50,000 does exist, but we were unable to find the successor for 50,000. Why? Search A, right? We were looking for the successor of predecessor. P is for previous. We were looking for the predecessor of 50,000. So this thing would have returned true, and then auto C head, C current equals head, and then we found the right thing for C, but is the way correct? While C's key is not equal to A, the thing that we were looking for. What we do is C's key, if A is greater than the current key, we go to the right. We go to the right. And otherwise, if A is smaller than the current key, we go to the left. That is correct. And then we see if the left pointer is null of this current key, because on the left we would have values that are smaller than C. Then if it is null, we have nothing on the left. We see parent. Does C have a parent? And if C's parent is not equal to null pointer, if C's parent is not equal, does not equal null pointer, then auto P equals C's parent. We take the parent out, and we are checking if the parent's right pointer is not equal to a null pointer, and if not, then the right value has to be equal to A. If it is equal to A, then we return P key, which is correct. If that is not the case, either in either of these two, then we return -1. Since we are looking for predecessor, that is correct. Else, if the parent is also equal to null, then we just return -1. That is also correct. And here, when left, c dot left is not null, then we find the maximum value on the left side, and we see if the parent does not exist. If the parent does not exist, then return the maximum value. Otherwise, if the parent does exist, I think the parent part is getting messed up a little bit. How are we doing in the insert function? Insert. If the head does not exist, then we create a head. Yes, creating the head is fine the way that we are doing it. Head equals make standard, make shared node, one, just one shared node, head, and put everything equals to null and put in the key. Okay. Otherwise, find while C is not equal to null pointer. P equals C, right? P equals C. And we can remove this from here, paste it here. P equals C. Previous is like this P node is kind of lagging behind C. And if A is smaller than the current value, we go to the left. And if A is greater than the current value, we go to the right. Otherwise, if we are at the current value, we break. And we are doing this before making our move. And we are also not checking if left and right exist or not in C. Yes, we don't have to. We'll just keep on moving till the end of the world. Okay. Else, yes. We have to change a little bit. Else, if we are at the thing that we were looking for, Then we have to do something about it. If C equals null, and then just break was fine. Break was fine. Break was fine. And if smaller, if A is greater, go to the right. And if A is smaller, then go to the left. Hmm, Yes, go to the left. Then we create a node. We put left and right equals to nothing, and we put the correct parent, which is also fine. And if A is greater than the current key, then we write it. We add A to the right side of the parent, otherwise to the left side of the parent, which is cool. I think the way that we are doing this part, that is not correct. P equals C, and then we are moving C forward, and we know that C is not equal to a null pointer, and C does not equal to A. So that is correct. That is correct. That is correct. Yep, that is correct. So what is the mistake? Let's use our LLDB debugger. Controls. Lang ++ LLDB BST. Let's use LLDB and see how this thing goes. LLDB, and we are going to set a breakpoint on the main function and run our function. And now next, next, next. It is asking for something. We insert, right? Next or quit. Let's say quit. We are going to create a breakpoint on line 241. Insert or add. How to add file in LLDs. File BST. Okay, and breakpoint 241 and run. Enter insert number, some random number. Insert. We are going to insert a bunch of numbers. Now we are going to look. We are going to insert, let's say 3000, and we will search if 3000 does exist. Does it exist? L number was found. Now we are going to find the next for 3000. Right. Step into this. Enter key. Next key. 3000. Now step into this successor function. And we are checking if head equals null. Next, head is not equal to null. So that is cool. Right. C equals head. Right. And let's print C's key. 245 is the key at C. Okay. 245 is the key. We went to the right. That is cool. We went to the left. So C's key must have grown pretty big. C key. 3600. That is cool. Next, C has been updated. What is the key now? Print C key. What is the key? 3500. So we will go to the left again. Yep, we do go to the left. Next, print C key 3400, and earlier it was 3500. Right. So let's do next. We will go to the left. We will go to the left. We did go to the left. Print C B. What is the key now? 2300. Now we will go to the right. We did go to the right. Now print C key 3400. We will go to the left again. Now print C key 3000 exactly. Now we are at the key. Now we are outside. Okay, cool. If C's right is not null, print C. Print go to C. Hmm. Hmm. The expression tried to call a function that is not present in the target. Print C. Print C is a node element pointer, 2 strong 1 weak. Print C left null pointer. Print C right null pointer. Print C parent is something. Print C parent key. Parent's key is greater. Wait, our binary search tree is messed up somehow. Yep, our binary search tree is messed up. No, shit, I messed up. It is not that the tree messed up, I messed up in implementing the tree. Like people who solve 18,000 plus problems. Shit, 18,000 plus problems. Shit. Like people who solve F and G, they have solved a lot, 80,000 plus problems, solving CP for many years. Wait, F and G in which division are you talking about? Because 18,000 problems is a lot. I have only solved about 260 problems. 18,000 problems is a lot. 18,000 is a lot. Oh, 18,000 plus in rating. Okay, that makes sense. Yeah, I guess you'll have to solve a lot of problems to get there. There is a structural mistake in our function. When we are looking for the successor, if the parent does exist, and if we could be the left child of our parent or the right child of our parent. This is our current node, and we could be the right child of our parent, or could be the left child of our parent. And if we are looking for successor, we need some value which is greater than this and greater than this. And if we have, when we are looking for successor, if we have a parent whose left value, whose left value, the parent's left value, then the left value in this part, then the smallest value that is greater than this value is going to be this value. Yep. Can it be smaller than this? No, I think. No, 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 no. Because the value on this side are always greater. Shit, binary search tree. This no, nah. Let's talk in order and pre-order. In order traversal. If our tree is like this, and we are looking for the left child of this thing, for the predecessor of this thing, and the predecessor of this thing is going to be this node, right? No, this node. Yep, this node is going to be the predecessor of this node, because if we go in order traversal, we will first have this node, then this, then this, then we will have this node, then we will have this node, then we will have this node, and then we will have this node. So this node is the predecessor of this node. This node is the predecessor of that node. So, how do we find something like that? So we keep going up the tree unless we find a left node. Yes, when we are looking for predecessor in terms of the parent. Okay. Let's fix predecessor search. If A does exist, then find A. Cool. Now C points to A. And okay, first let's find the parent. Auto P equals C parent. The first left node. And if there is no left node, if there is no left node, then we are doomed. Then there is no, yeah, there is nothing. There is nothing there. While P is not equal to null pointer and P val equals -1 initially. If we know that P is not equal to the null pointer, then we will have auto P equals, let's start from C. If it is not equal to the null pointer, then we will see, we will take the parent, let's say, in or auto x equals P parent. Yes, we have the parent. If x is not equal to null, or if x equals null pointer and still we haven't found anything, then break. But if x is not a null pointer, then we have to check if x has a, if the parent has a left child or a right child. We are at the parent, we need to know which child we are. If left, okay, let's first test for the ideal case. In the ideal case, parent would have a right child is not equal to null pointer. If it is not null pointer and x right key is p key, then we have the correct value. P val equals x key and break. Else, if that is not the case, If that is not the case, then p equals x. If then p equals x, then p equals x. Yep. Now we have the value for the parent, which is p-val, and let's also say int mx equals, we need the maximum value on the left child because we are looking for the predecessor, maximum key on C left, and return depending on which one is smaller. Now, if mx is not equal to -1, if both are not equal to -1, if any one of them is -1, if either mx equals -1 or p-val equals -1. If that is the case, then return if mx greater than p-val question mark. If that is the case, then return mx, then otherwise p-val. Else, if both of them, if none of them is that, then return mx greater than p-val. If p-val is smaller, then we will return previous value other than or mx. I think that works. I think that will work. Help us finding the thing predecessor. Stuck at 1440 in code forces, but mostly EFH problems are 2000 plus rated, so it is not easy to solve. Yep, they are not easy to solve. Maybe he's talking about a lower division. Yeah, even in div 3, I guess they are higher rated. Do you study things randomly or do you have a schedule? Like I need to study book today, or yes, I do have a schedule, and it is hard to follow the schedule. Right, it is hard to follow it, but yeah, I do have a schedule. Yo, how are you? Building logic, I am unable to solve programming coding problems. Building logical skills. Eric, what would you like to say about that? I would suggest I would say when I didn't have any logical problem solving skills, I mean, still my skills are not great, but they are much better than they were before. This is the thing that I solved. Advent of code. This thing gives you questions and you have to solve them, and then when you have found the answer, you have to input your answer. Your answer could be a number, could be a string, anything. You have to input your answer here, and the way that they present question and the way that you have to solve question is pretty intuitive, and I think this is pretty cool if you want to improve your problem solving skills. This thing, a really good roadmap for ah I will check it out. I have seen that website, but I haven't checked it out like deeply what it means and what the things there are. I have read a thing on Reddit about competitive programming. I guess this article, and this article gave me the things there are in this article. Those are the only things that I have used in my competitive programming learning thing. And yes, shit, this article is a bit long, but yeah, this is pretty cool. Competitive programming guide. And Eric, we are creating some binary tree, binary search tree, and I think this is going to help me in understanding how things happen under the hood. The other day we were talking about associative data structures. This is not good because binary search tree is not balanced. So in some future video, we will also create red black trees, which are used under the hood in C++, and that would be pretty cool. That would be pretty cool. And right now we have created a bunch of functions, and the ones that we need in a binary search tree are these. And among these, we have written the search function, the minimum and maximum function. We have written a function for insertion. For insertion, we are fixing our implementation of successor and predecessor function, and then the delete function. Delete function is the most complicated among the all of them, but after we have implemented successor and predecessor, deletion would not be that hard. That is the goal. Heaps are fun to implement as well. Shit, heap. Okay, yes, I will also do something with heap. Heaps are fun. Heaps are fun. Okay, I think yeah, predecessor does work. We are searching, and this might be very stupid implementation. We search here if the current node exists, the node that you are asking a predecessor for. And the thing is, we are only returning a predecessor or a successor if the current node is a part of the search tree. This does not work like the lower bound and the upper bound function in C++, where you just give a value and they will return the appropriate answer. So that is some difference. And then this logic is correct. We are finding the node if it exists, and then P parent. So this part of the code, put some value in pval, and pval returns the value of the first parent, first ancestor, which has a left child. Uh, uh, a diagram would be better, since we are looking for predecessor here. In this function, we are looking for predecessor. Then if this is the thing, this thing, if stuff is like this, then if I want the predecessor in terms of the parent, then this thing is going to be the predecessor. Wait, no. If the left child does exist, then it is going to be the predecessor. Shit, if the left child does exist, then it is going to be the predecessor. I don't need the parent. If left equals null, or let's say if it doesn't equal to null pointer, then that is going to be the answer. Return C left key. But now if it doesn't exist, then return whatever the p-val is. And p-val, we are starting from the current node, and we are seeing if it is not a null pointer, then we take it the current node's parent, and we are checking if the parent does exist. If the parent doesn't exist, then break. We can simply break without updating p-val. And if the parent does exist, then we see the right child of the parent is not equal to null, and the right child is the current node. If that is the thing, then put that parent's key equal to pval, parent value, previous value, and break. If that is not, then make x our current node and repeat the same procedure with that. And then at the end, return pval. And we are using -1 to represent not found, which is not a very good thing. We should use something like null, but I do not know if I can return something like null here. Does null exist in C++? Yes, I cannot. Yeah, we cannot return null. It is just -1. Cool. Predecessor, go left once and keep going right. Lots of cases of handle. To handle. Yep. I use Mac, and go left and keep going right. Yep. Once. Yeah. Go left once and keep going right. Yes. This is correct, right? For the predecessor, X right if right does exist. For the current parent, right? Uh, for the parent, if we are currently here, and for this thing, we are checking if the right does exist. If the right exists and it is equal to the current node, then cool, return the value of this node. And if none of them exists, if none of them is true, that is either the right child does not exist or the right child does exist but it is not equal to our current node, then also move our pointer to this node. Then this, oh yes, keep going right, right? We keep going right, and once when we move left, we return this thing. That is what we are doing here. That is cool. That is correct. While C key, yep, here we find the thing. And after that, now we need the successor. Successor, if the right child does exist, if C right isn't equal to null pointer, then return the minimum value. We have written a function which finds the minimum value for a given node. Find the minimum value for right. That is going to be the thing. But if it doesn't exist, if the current node does not have a right child, then the successor is going to be, we keep going left. Yeah, we just keep going the opposite way. Auto P equals C. And P val equals -1. While P is not equal to null pointer, what we will do is auto X equals P dot parent, get the parent for P, and if X equals null pointer, then break. Otherwise, if X does exist, then we need to make sure, then we need to check if X has a left child. If X left is not equal to null pointer and X left P equals P key. If that is the case, then P val equals X key and break. If that is not the case, then P equals X, move back, and here return P val. Let's see if it works. Dot slash BST, insert some numbers. I messed up with the number there above. Yep. Again. Now let's enter 4,000. And what is the next for 4,000? Next key is 4,325. Okay, that is working. What is the previous key for 4,000? Previous key is 9,082. So that is working. That is cool. Now when you climb back up the tree, yep, not when you climb, if you are trying to find the successor of a node and it has both children, then you need to go to the left child and keep, yep, what that is what I'm doing. If I'm, wait, successor, and then go to the left child. Left child is going to be smaller than the current child. Yes, predecessor. Then you need to go to the left child and keep going to the right child. We just need to find the minimum, right? Here in the predecessor. If left is not equal to 0, shit, yes, 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 shit. How did I mess this up? Return minimum key for C left. whatever the minimum key is from there. Shit. Okay. Or maybe minimum key from C also. That would also work. Shit, how did I mess that up? Even though I didn't. Here I have to look for the maximum key. My bad. Wait, no. Uh, Here I just have to look for the minimum. No, this is fine. This is fine. Here I have to look for the. How am I messing this up? Here I have to look for the maximum. When I am looking for the predecessor, I have to look for the maximum key on the left, because every key on the left is going to be smaller than my current key, and I want the key that is the highest among all those smaller keys, right? And maximum is just found by going to the right, right, right. We'll keep going right, right, right. And here we will find the minimum among the right. That would be when we keep going left, left, left. That is cool. Right. Max key from left side. Max, yep. It is max key from left side because you are trying to find the node with the largest value smaller than the current key. Yep. It works. Maximum key on the left side. Cool. It's did we got the right answer here? Yes, we did got the right answer here by chance. And let's also write the option to quit this. Shit, exclamation mark to quit. Now, if at any point C equals exclamation mark, then exit with function with code 0. Clang dot slash BST insert. We messed up a little bit. Dot slash BST. Insert a bunch of numbers. Insert this number, insert this number, insert this number, insert this number, insert. Let's say insert 1, insert 2, insert 3, insert 4, insert 5, insert 6, and tell me the next number for 5. For 4. The next number for 4 is 5. That is correct. And what is the previous number for 4? That is 3, which is also correct. Let's quit. Quit. That is working actually. So that is cool. And I'll be right back. I'll just go to the washroom. I'll be right back. Yep, I'm back. And everything seems to be working just fine. All we have to do, we have implemented all the functions, all the methods, operations that we need. We have done successor and predecessor also. Now we need to do deletion. That is cool. Now we need to do deletion. How do we do deletion? Okay. We know the properties of a binary search tree. Let's say our tree is like this. We have to figure this out. And after we have done all these operations, we will make our library a bit library. Yes, we are calling this library. We will make this a bit general so that we can store other things other than integer. Right? Here it is just integer. We will use some template types, generic templates. So let's say we want to delete this node. What do? We want to delete, let's say we just delete this. If it is a leaf, then cool. If the current node is a leaf, we can just remove it, no problem. But if the current node has a left child, what do we do? Okay, how many conditions there are? If the current node is a leaf and has no other childs, then just delete, cool. And if the current node has a single child, either left child or a right child, then whatever is the parent of this thing, we just attach this thing to the parent, right? Nothing too fancy. But if the current node has two childs, then what do we do? And also we have to check if the parent here is null. If the parent is null and this thing therefore is the root, and this thing has nothing, just a single child, then this thing will become the root. And here also this thing would become the root if this is the root and the root is the thing that we are deleting, right? But if the current node has two children, what do we do? If we remove this, okay, let's say the parent node is on the left, that is this value is smaller than our current node, and our current node has two children nodes, and we delete this. Now what do? We have deleted this. I think we can attach this one to this and this one to this. Something like if we label these things 1, 2, 3, 4, I think we can convert this into something like 1, 4, and 3. But what if this thing has something on the left? That is a serious problem. So we find the smallest node, the minimum value in this node, and whatever that node is, we attach this node to that, and we attach this node to that. That is cool. That is cool. That is what we can do. And would there be any other problems? If the other condition would be if we are the left child of a parent, and I'm just theorizing, if we are the left child of the parent, then the parent would have a higher value than us. Then we can maybe add this node to this, make this node the new left child since we have deleted this, and attach this node to the leftmost node, which is the same as this, which is the same as this. Yeah, which is the same as this. So we can make the right node the child of the parent, and we attach the left node to the smallest node on this right node. Okay, and I think I got that right. What is the difference between bootdev premium and freon? In bootdev premium, in free version, boot.dev, in free version, you can, in every course you can submit your solutions to only some things. What the heck? Boot.dev, why is it HTTP? In the free version, you can only submit your solutions for some exercises, 5 to 6 or maybe some number of exercises at the start. But in premium, you can submit your solution and get them checked from for all the exercises, and that is the only difference. But even in free, you get access to all the content that there is. The only difference is that you are unable to check if your solution that you have written, if it is correct or not. That is the only difference. After insertion, deletion, right? Deletion does not return anything. Binary search tree, remove, and int a. Okay, what is that? Remove a. Yep, this function could be called with a, and when it is called with a, we have to check if first we have to find a. Yep, if search a, if a does exist, then we have to find a. Auto equals head, and yep, head while c is not, key is not equal to a. While that is the case, c. If c key is the current key is lower than a, then a is on the right. C equals right. Else c equals c if a is smaller. Then we find a. Now we know where a is. Now we have to check the number of children that a has. If a, if c dot left equals null pointer and c dot right equals null pointer, then we can just remove this thing, substitute dot like literally a dot with this sign on the whole line. Cool. Vim, that is what you call vim. And if that is the case, check if head is c. If head, if c equals head, if c is the head, then c dot reset and head equals null pointer, not equals but equal to. Else, if that is not the case, then go to the parent of c and yep, just yep, c parent, which child are we of our parent? If c auto p is the parent, and now that we have the parent, if parents left child is not equal to null pointer and parents left child's key is c dot key, which is a. If it is a, then p left equals null pointer, right? Else, if that is not the case, then we must be the right child. P right equals null pointer, and at the end c dot reset. Okay, we have freed the memory. At least I think we have freed the memory. This would be the case when none of the child exists. Now, if there is a single child, if left equals, and after this we can return. If left equals null pointer or if left equals null pointer, if just one of them, XOR. Shit, that is cool. That is cool. We can take the XOR. We can take the XOR. XOR right equals null pointer. If that is the case, only one of them is true, then auto p equals. Now first we check if C is the root. If C equals head. If C is the head, if C is head, then whatever that child is, then head we first change head. Head equals whichever child exists. So C left equals null pointer. If left is null pointer, then head will be equal to right, otherwise left. And now head has the new value. We can do C dot the shit. I am very stupid. I am very stupid. We also have to update the parents. We also have to update the parents here. Yep. If no parents, then this. And if it is not the root, then find the parent. And yes, that is correct. If C left is not equal to null pointer, if left is not the null pointer, then left is the thing. Head equals C left, left, and C left parent equals head. Yeah, null pointer, null pointer, null pointer. Else head root equals C's right pointer, and C's right pointer's parents is a null pointer now. And at the end of both the cases, we do C dot reset since we deleted C. Now, when we know that C is not a head, and here we can return. Now, when we know that C is not a head, what do we do? When C is not a head, we find parent. C auto P equals C dot, yeah, it is not a function and it is not even, it is a pointer to a struct. Uh, how do you study a topic, bro? Study randomly or study when you encounter the topic? Like I was practicing question. I faced 5 to 7 graph problems, but I didn't know nothing about graphs. Yes, it is like both of the things. I know that I'm bad, generally speaking, at maths in competitive programming. My maths is not up to the par. It is not as good that as I would like it to be. So I'm studying maths side by side, studying about maths on side by side, and also whenever I encounter something, like I also encountered or saw problems of graphs and dynamic programming, which I was unable to solve. Then I did some thing. I read about graphs and dynamic programming, and then I was able to solve them. So that was cool. So both the things. It is. And now we have the parent here. C's parent. Now we have to check which child it is. If P left is not equal to null pointer. Wait, okay, let's do this. a test program. We will write a test program and test.cpp and main standard out is null pointer equal 0. Client plus plus test.cpp. That is true, so we don't have to check for null pointers. If p dot left, if the left side of p does exist, then check if p left key, or a more better way, since these are just pointers, if left equals c. Okay, that is a much better way to handle this. If p's left does exist and left is equal to the key, then we do the above thing here, the whole thing. Now we know which side of the parent we are. We have to find, not find, yes, we have to find c, which child c has. C has only one child. So if c left, if there is the left child, then we update the value of the left child's parent. C left parent will be equal to p. Yep, we have changed the parent, and p's left will be equal to c's left. Huh, that is cool. That does work. Then c dot reset. C dot reset would happen anyway. Else, if that is not the case, if C has the right child, then C's right child's parent is going to be P, and P's, well, this thing is, no, this thing is not common. P left is going to be C's right child. I think, hmm, 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 hmm. This thing is cool, but this part we can skip. Auto X equals, if C has a left child, then C left. Otherwise, C right. And we can skip this whole thing and say whoever the child is, their parent is P now, and whoever the parent is, their left child is X now, and reset C. What is that? C dot reset. We can do it here. C dot else and X dot parent is, why do we have 0 here? The parent of that child is going to be P, and P left or right equals X. Now that also seems very repetitive as a programmer. Mm. That is much better. That is much better. And then reset P. This was, and then now when we have both the childs, yep, when we have both the childs, then we have to do some more work. We will go to the parent, and whoever the parent is, either it is head or it is not the head, we will make the right child equal point to the parent. The parent will point to the right child, and this thing, the left child will go to the left side of right side of the right child. If not if C equals head, if C equals head, then head equals C right. Else, if C is not head, then auto, then check the parent, which side of the parent we are on. Wait, we can actually make it a reference. Auto. Wait, if we can make it a reference, then we can fix some things here. Auto reference, auto reference P C, PC as in like P child would depend on P left, P's left child exists, and that left child, if it exists, it is equal to C. If that is the case, then P left, otherwise P right. And here instead of all of this, we can say PC equals X. P's child equals X. Okay, and I think we can do much better here also. Auto reference PC parent's child is going to be equal to if C equals head. If C is head, then it is going to be equal to head. Otherwise, we have to check a few things. We have to go to the parent itself. Yep, we have to go to the parent. C's. I think that would be pretty bad. Makes sense. So if C equals head, then head equals C's right child. Head equals C's right child, and C's yep, and C's right child will point to null pointer. No, C's right child will point to C's parent, whatever that is, whoever that is. Right, right child's new parent is going to be C's parent. Current node's parent is going to be C's current parent, if it is head or whatever. Else C's parent, we have to see which child C is. And do we need that thing ever again? Nope. Auto P auto PC equals C's. I guess we can use auto P equals C's parent, and auto reference PC going to be the same thing as above. P, if P has a left child and that left child is C, if that is the case, then PC is going to be P's left child. Otherwise, P's right. No, 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 no. Okay, yes, should I mess up here? Dot left. This will return me the pointer. Okay, this is fine. This is fine. PC equals to C's right child. Right is a pointer. Yeah, yeah, that is cool. That is cool. We have updated the parent, C's parent. Either it was head or not, whoever it was, it is now pointing to C's right child. Right? C's right and C's right child is already pointing to C's parent. And now in this code, C, if C was head, then head is pointing to C right. And if C was not head, then we found the parent for C and made sure that that parent is now pointing to C's right child. Now all we have to do is go to the C's left child. This is the current node. All we have to do is go to the C's left child, this thing, and find the minimum node here, whatever it is, find it and make their child, left child, equal to this thing. We can just call the minimum function on this right node. Int mn equals minimum key, or we can just auto mn is C's right child, and yep, auto, yep, and while C has a left thing to go to C, uh, while mn has a left place to go to, we will put mn equals mn left, and all that is left to do is C left new parent is going to be mn, and mn should, and mn's dot left side is going to be C's right child, C's left child. Yeah. We have taken both the nodes, and in both the nodes, we have changed their parent. Yep. For the right node, we have changed its parent, and right nodes, we have also changed the parent's child to be equal to the right node. And in this part, we have changed the left node. We found the minimum node to C's right node, and we have changed C's left node's parent to point to the minimum node, and that minimum node's left child is now C's original left child. So that should be correct. And now I'm charging my phone. Wait a minute. Yep, that is charging. Cool. I think, hope that makes sense. How did you overcome the missing submissions of boot dev? No, I just thought, shit, the difference between trying and doing. Okay, that is a philosophical one. In boot.dev, the problems for which I was unable to solve the submission because I didn't have a premium subscription. I just skipped those problems. I did solve those problems on my own, but I didn't check. I mean, I thought I am doing the right thing, so that is cool. Just have to believe. And what is the difference between trying and doing? When you are trying something, I have seen this with myself. When I am trying something, I'm just making a show that look at me, I'm trying to do this thing. And if I am unable to do this thing, then that the mistake the mistake is of that thing. And there is nothing wrong that I did. The fact that I'm unable to do this thing, the thing is to blame, not me. If I'm trying to solve graph questions and I'm unable to solve them, then the blame is with graphs. They are too hard for me. It is not my mistake that I'm unable to solve them. It is graphs' innate property that I'm unable to solve them. That is the mindset when I am trying to solve a thing. But when I am actually solving a thing, then whatever happens, if I am able to solve a thing or unable to solve a thing, everything is on me. If I cannot solve DP questions, then that is on me. It is not because DP is hard, it is because I'm not trying hard enough, or I'm not, yeah, trying not hard enough, or not reading stuff from the internet, or not watching enough videos on it, or not practicing on it. It is my mistake if I'm unable to solve DP questions when I'm actually doing it, when I'm not trying, when I'm not making a show of it. So, yeah, so you don't just have to try, you have to actually do the thing. You can look at Charles Bukowski, Tombstone. Okay, this, don't try. It says, don't try. Don't try, actually do the thing. Don't try. So don't try, actually do the thing. And yep, today just doesn't feel right, but I'm going to do this anyway. Okay, this seems like correct. Yep, this seems to work. Let's try if it actually does work. Let's have the deletion operation here. Delete. Even though internally the delete operation is called remove. We will have a condition here as if C equal delete. If C is delete, then C, which node do we have to delete? Enter node to delete, and then C in A, and then call the function. Yeah, just call the function. There is nothing that we have to actually say to them. So yeah, we don't even have to return anything. And this is bad. When we insert, we are doing that. And when we search, add a new line here. and see out a new line at the end anyways. And here when I have a b dot remove a and then see out or put char 10. Put char 10. Put char function takes in a character and puts it on the screen, put char. And 10 here is the ASCII code for the character new line. So this is going to put a new line, not test. Clang plus plus binary search tree dot cpp BST with the G flag dot slash BST. Let's insert 5, insert 10. Let's quit dot slash BST. Let's insert 1, insert 2, insert 3, insert 4, insert 5, insert 6, insert 7, insert 8. 8. And now let's delete 5, right? And delete 3. Now what is the next node for 2? Next node for 2 is 4. That is pretty cool because we deleted 3. What is the next node for 3? No next node because 3 does not exist. What is the previous node for 4? Previous node for 4 is 2. Deletion did work. What is the next node for 5? No next node because 5 does not exist. What is the next node for 4? 6. That does work. Now let's quit because the way that I inserted the numbers, it would just become a linear linked list. So we have to be a bit smarter. Let's add 1, then 2, then 3. Let's try to have a structure like this. Make a node here, a node here, a node here, and a node here. Say 1, and then 2, 3, 4, 5, 6, 7. How do I insert them? First I insert 1, it will go there. Then I will insert 2, it will go right here. And then I will insert 4, it will go right here. Then I will insert 3, it will go here. Yep. And then I will insert 5. Then no, then I should not insert 5. I should insert 6. I should insert 7 so that I will have this thing. And then I will insert 5. BST and dot slash BST binary search tree. Input 1, enter 2, enter 4, then enter 3, enter 6, insert 7, insert 5. Now, what I'm hoping is that this is the internal structure that we have. Now, if we delete this thing, and I should also write a function a method which can just print the whole tree. Anyways, here, if we delete this node, then we should have something like this. The left side would be the same, but on the right, we would have 7, 5, and 4 here. So for 5, the successor would be 7, and the predecessor would be 4. Let's check the predecessor and successor for all of these things. Delete 6. Now that we have deleted 6, let's check. Next for 5 should be 7. It is 7. Okay, it does work. And previous for 5 should be 4. It is 4. That is also cool. And if we check next for 7, no next node because 7 is the greatest. Previous for 6 or anything for 6, search 6, number is not in the tree, that is cool. And if we see previous for 7, it should be 5, it is 5. Okay, so it is working. Next for 4, it is 5. Okay, yeah. So yeah, our BST implementation is complete in that sense. All of these operations work. Our BST is working. We have done completed all of these things. But now there are a few problems that we have to address. First, we have to make our binary search tree generic. Right now, it can only store integers, but we want to make it store integers, strings, and characters, and smaller values like that. Built-in, no, string is not built-in, but the values which types which we can equate, which we can compare. And if standard compare does not exist, then the user has to provide a compare function for them. Generic, first we have to make, not first, we can make it generic later. And the second problem is destructor. The destructor for our class is not very smart. This thing, destructor is not very smart. It is very dumb. It is not even doing anything. It is just freeing the head pointer, which essentially means if we have our tree, our whole tree, this destructor is very dumb. This destructor is just freeing this node, but all of these node are still in the memory, so memory is leaked. So we do not want that. So we want some recursive function which will take in a node and do some DFS stuff and clear all the nodes. Let's write the function. Void, it won't return anything. Clear DFS, and it will take in a shared pointer, std shared pointer, not like that, shared pointer to a node. Let's call it P. Now, if P dot, let's first write the base conditions. If P dot P's left equals null pointer and P's right equals null pointer, then P dot reset and return. Else, if P's left, then clear DFS on P's left, and if P has a right thing, then clear DFS P's this pointers right child, and at the end P dot reset. And what we can do is if head, if head is not null, then clear DFS on head, and yep, there's this. Can I define the destructor outside? That would be crazy. I guess I just have to do this. BST, non-static member function. Mm, I guess I have to do void BST this operator this BST cannot have a return type. Okay, that does work. That works. So when this if head, then clear DFS with head. Cool. Now our destructor is also fine. Our destructor works. So we can cut this thing off. This thing is done. Now we have to make our class more generic so that our nodes can store values which are not integers, non-integral values. So therefore we have templates, type name T, and also a function class compare. Type def requires a name. Here is the name. Template type name T. Type def require is this thing? Declaration does not declare anything. Okay, I don't know how to use template. How to use templates C++. Template type name entity definition. Okay, the definition has to come right after it, I guess. Too many errors omitted. Okay, I guess we don't have memory. No, it is not a template, is it? Template T. Struct class templates. Template this before class. Okay. Inside public, I can use it throughout. Template type name T. So this should have what? Type def struct node using node equals to struct node. Okay, cool, that works. Using node equals to this structure, and now at least that is generic. Template, type name, we need T, and we also need a function which compares things. Class compare, right? And the initializer will take in, wait, I need to ask a question. When we pass something to a thing like vector and we pass it like this, where does it go when you pass something like this? When I pass a type to a STL function like vector int, not function exactly, but yeah, you get the thing. Vector int how in my implementation of a I capture this type. How do I get this type? That was very slow. If someone passed this, then how do I capture this inside my class? Void print my class. Print type size of t int obj print type size of t. How are they able to get this t? Wait, to just get it here, t becomes vector int t. Okay, type name t. That now it makes a lot of sense. Template, now it makes a lot of sense. Everything that I define inside a template goes there, goes inside the library. That makes sense. This should also have given me error, I guess, when I was initializing this structure, I guess. But that works just fine. And I'll have to go to the washroom. I'll be right back. Question description in the video. I'll be right back, right? Yo, I am back, and this question is from your description of the video. Yes, it is the same thing. Charles Bukowski is also mentioned there. Charles Bukowski is a nice guy, amazing person, even though he's dead, but that does not matter. He is still amazing. And JB, I guess, good job. Thank you for that. Okay, now we want to make our class generic. How do we do that? We have taken int everywhere. Let's change that to be equal to t. Substitute int to t. Okay. Now our class is at least generic, and DFS function. Okay, that does not need to know anything. Search. Let's apply, make search generic. Template, type name t, and instead of integer in the whole thing, we are going to substitute that with t. Okay, that was the only thing. And what is the comparison function that we are going to use for this? How do we... Yes, uh, we fix that from here, CMP. We will head, we have a head. Head is this, and we will have a comparison function. Wait, is the LSP not working? Shit, the LSP is not working. But I'm not getting any errors. That is bad. No errors, no errors, no errors. Client, why did the client quit? Restart the LSP, and there is no LSP. And signal 11, okay. Uh, n dot local. Okay, so we have some bug that we have to fix. The LSP is not working. We have to fix the LSP. Local state nvim lsp dot log. Now that we are here, shit, that is a massive error. Please submit a bug report. Shit, that is something very bad. What is this? And why is this file so big? Okay, so what we can do is, first of all, delete the log file. That is what you do. Delete the log file. It is very big. We don't want that big log file. Attach to DSA thing, TDSA, target is DSA, and we quit and we restart and we do get an error. So we will go to local state neovim lsp log, and what is in the log files? There are 16 lines, and this line seems to be the last one. And you can see that every line here says error. That is because the mode of communication between LSP and neovim is through standard error and not standard input. See, standard error. They communicate through standard error. So even if this is a right message, there is no error. We will see here error because they are communicating through standard error and not standard input and output. Okay, please submit a bug report, including the... Please submit a bug report to http github homebrew. Homebrew. Shit. How is homebrew messing up? And include the crash backtrack trace stack dump at whatever this location is. Shit. I guess we have to work without the LSP for a while. LSP just broke. LSP ain't working. LSP doesn't work. Well, at least the binary tree is fine. All the operations are working in the binary tree, the binary search tree. It can search, it can find the minimum, it can find the maximum, it can find the successor, it can find the predecessor, it can do insertion, it can do deletion. And we have no leaks in our code. There is no memory leak in our code. Go to search, find t, find t, make this an integer, and change here everything. Substitute from t to an integer in the whole line. Okay. Yep. What is td in, and here also, and here also, null pointer int, and where do we have int minimum successor inserter, and here also. Cool. I guess that is pretty cool. That is pretty cool. Our BST is working. Our binary search tree is working. It can do insertion. It can do searching. It can find the minimum, the maximum key, and it can find the predecessor. It can find the successor, and also it can remove a node, which was the most complicated operation in the whole thing. How many lines have we selected? Okay, so the deletion operation is written in 61 lines. That is quite a bit. And then at the end here, we have the simulation for the whole thing. That is cool. That is cool. And that does work. We have written our own BST, binary search tree. And for today, that would be the end of today's stream. And thank you for being here. Bye.